Hello everybody, I hope you guys are doing well. Today I'm here to talk about the eigenvalue problem. Let me see if this is okay. Okay, eigenvalue problem. So the idea is we have a lot of problems around us and we see those problems as in the form of data. Data means numbers. We are so much interested about the pattern or dynamics in those numbers. So the flow of information is exactly what we are trying to work on. So let's get into what we have up here. A lot of dynamic problems around us. We have numbers, meaning data, and our objective is to identify the pattern that emerges. And eigenvalue and eigenvectors, they both together help us crack the dynamics of the data. Let's begin with the concept. What exactly do we mean by the eigenvalue problem? What is an eigenvalue? What is an eigenvector? This is the formal definition of the eigenvalue problem. Here, so we can see A times x equals lambda times x. A is an arbitrary matrix, lambda is the eigenvalue, and x the eigenvector. Maybe it would make a lot more sense once we get into the example down below, down here. In the example below, we have this random matrix A starting with 0.8 and then 0.3, 0.2, 0.7. Such matrix is called Markov matrix because each column vector in matrix A is a probability vector. What I mean is the sum of the entries in each column reduces to 1. So 0.8 plus 0.2 equals 1. 0.3 plus 0.7 equals 1. So 2 points to be noted for Markov matrices are each column in a Markov matrix is a probability vector. The entries would sum up to 1, and each entry in a Markov matrix would be a positive number. So this is the matrix. This Markov matrix is the matrix we would be working on. We'll try to find the eigenvalues and eigenvectors for this matrix right here. We have the matrix A, 0.8, 0.3, 0.2, 0.7. At first, our aim is to find the eigenvalues in order to do so, what we can do is we can set the determinant of this matrix inside to 0. So determinant of matrix A minus lambda times identity matrix would be 0. So determinant of, here we have this matrix A minus lambda, and then I is the identity matrix, must equal 0. And then we just move on, perform the algebraic calculations, and we end up, we keep on moving till we get to this point. We have a polynomial lambda squared minus 1.5 lambda plus 0.5, which is equal to 0. This can be easily solved, and we end up with eigenvalues of 1 and 1/2. So 1 is the first eigenvalue and 1/2 is the second eigenvalue. These are the eigenvalues, and next what we plan on doing is we will try to find the eigenvector corresponding to each eigenvalue. That means the eigenvalue of 1 would have its own eigenvector, and the eigenvalue of 1/2 would have another corresponding eigenvector. So next we look for the corresponding eigenvectors. We need one eigenvector for this eigenvalue and another eigenvector for that eigenvalue. Okay, let's just start and then I can fix the page once we get to the end. And now eigenvectors. So eigenvectors they're actually vectors that lie in the null space of this matrix right here, A minus lambda I. Okay, let's do that for the first eigenvalue, which we had as 1. So first eigenvalue was 1. Let's try to find the eigenvector for this eigenvalue. So we have A minus lambda I. We start with A minus the first eigenvalue times the identity matrix, and as I said earlier that we should work in the null space to find out the corresponding eigenvector. So A minus the first eigenvalue times the identity matrix times some vector, and this is the eigenvector corresponding to this eigenvalue, is equal to the 0 vector, and then A, as you know, it's the Markov matrix, minus the first eigenvalue, which was 1, times the identity matrix. So we're done with what we have inside the parentheses, times this vector, and like I said before, this is the eigenvector for the first eigenvalue, and then is equal to, so we can expand this 0 vector and write it in this form, a vector containing all zeros. Then we just perform, like, do the algebra. We have from this, we have this matrix, and this matrix times this vector must give us the 0 vector. Then I wrote this eigenvector using two unknowns a and b. So eigenvector x of 1 is essentially equal to the vector containing a and b. So what we have right here is a system of two linear equations. I hope you guys do know how to solve a system of linear equations. Once this system of two linear equations gets solved, we have the solution right here. So a is equal to 0.6 and b 0.4. So that makes the first eigenvector equal to this vector containing 0.6 and 0.4. So this is the eigenvector corresponding to this eigenvalue, or you can say that so yeah, that's basically the idea, that for a given eigenvalue we must have an eigenvector. Afterwards we just work with the second eigenvalue. Again, we do the routine work. We start with a. Let me fix this a little bit. We start with a minus the second eigenvalue times the identity matrix times this eigenvector. Note that this eigenvector is the eigenvector corresponding to this eigenvalue, 1/2. So okay, a minus the second eigenvalue times I. This is the a minus second eigenvalue was 1/2, so we have 1/2, and then I is the identity matrix. This is just the second eigenvector. I mean the eigenvector corresponding to the second eigenvalue. Next, it's just all algebra. At this point, I wrote this x sub 2 eigenvector as a vector containing c and d. We solve this system of two linear equations and we get 1 and -1 as the solution. So x sub 2, vector x sub 2 is equal to the vector containing c and d, which is equal to 1 and -1. So x sub 2, which is equal to 1 and -1, is the eigenvector corresponding to the second eigenvalue, which is 1/2. So these are all we do to find out the eigenvalues and eigenvectors for an arbitrary matrix. What we have done here is we worked on the eigen-decomposition of a matrix, of a special matrix known as Markov matrix. Thank you.